Hello, everyone. Thank you for attending the webinar today. My name is John Stancarone, and I'm an engineer and product specialist with T-Equipment. We have a really great webinar for you today. We've got Will White, Senior Application Specialist, DER with Fluke, who will be presenting advanced test techniques for solar installations. Now, Will is a seasoned professional in the renewable energy sector with over 2 decades of experience spanning installation, sales, design, product management, curriculum development, and teaching. He began his career in 2005 as an installer with a small solar integrator, and over time, as the company grew, he expanded his expertise across sales, design, project management, eventually serving as Director of Operations for the East Coast. Now, in 2016, Will joined the curriculum development team at Solar Energy International, where he helped modernize and expand course offerings while teaching both in person and online. And after 5 years in curriculum development, he transitioned into the role of Director of Business Development, where he worked closely with clients to identify and implement tailored training solutions. And since 2022, Will has served as a Senior Application Specialist at Fluke, supporting the company's renewable energy testing portfolio, including IV curve tracers, electrical meters, and thermal imaging cameras. His technical area of focus is distributed energy resources, including energy storage, electric vehicle supply equipment, and photovoltaic systems of all scales. Now, before turning the presentation over to Will, while we're waiting for any late joiners in the webinar, I have a couple of slides about our company that I'd like to share with you. We have recently celebrated over 20 years in business, and in that time, we've become a very large stocking distributor. We really do take to heart the slogan, buy from the people, not just the internet, and we have a qualified staff here to help you. As you can see from this slide, as a national and international distributor, we cover the needs of a wide variety of customer types on the left. On the right, you can see some of the product and instrument types we do carry. In total, there's more than 500,000 different products. Now, as you can see from this slide, we have invested heavily into making our website a great resource for our customers. You can see on the left, we've got filtering capabilities by specifications to narrow your search faster. There's a lot more than that too. I've just basically shown the categories and the price ranges, but there's many more depending on the product in question. You'll see a lot of different things you can sort by and eliminate things that aren't of interest. So that's really useful, and we think it's going to be very helpful for you. So it's now time to turn over the webinar hosting to Will. Will's going to be taking it from here on. Now, if you do have questions, please do submit them via the chat. We'll be happy to answer them at the end of the webinar.
Thanks, John.
Well, you're very welcome.
Let me show my screen here. Oh, that's the wrong screen. Just 1 second here. Okay, there we go. So again, thanks, John. My name is Will White, Senior Application Specialist for Distributed Energy Resources at Fluke. I cover all of our renewable energy products. And in this presentation, we're going to go over a couple things. The first thing we're going to talk about is the GFL 1500. This is our new ground fault locator. We'll talk about ground faults, why they matter. We're going to go over the hardware. We'll talk about the different functions and modes of the GFL 1500. This is a brand new product. We just released it at RE Plus last week. So exciting to have this on the market. Then we'll talk about the PVA 1500. We'll go through IV curves, what an IV curve is. We'll talk about very briefly the PV Analyzer software, which is the interface for the PVA 1500. And we'll go over how we measure temperature and irradiance when we're doing IV curves, and then how to actually take an IV curve test with the PVA 1500. And then we'll have some time for a question and answer, hopefully at the end. Starting off with the GFL 1500, what's a ground fault? A ground fault is an unintended connection between a current carrying conductor, like a DC positive or negative, and a non-current carrying grounded metal part, like the frame of a module or a piece of racking. In this example, we've got a ground fault in this photo between this wire and the metal wire hanger. So now we've got current flowing to ground. Ground faults are a safety hazard. If we have current flowing to metal parts, then they may be energized. If we touch those, we may get shocked or electrocuted. Ground faults are often arcing, so that arcing can create sparks and heat, which may lead to a fire. It's also reducing the financial return on the system. If an inverter has identified a ground fault in the system, the inverter will shut down. That means we've lost production from that inverter, and that could be a portion of the system. It could be the entire system, depending on how big that inverter is. Also, I've got current flowing to ground instead of going to the inverter when the inverter, if the inverter should be operating, so I'm losing production there. There's two types of ground faults, solid ground faults or a low resistance connection. The connection is always present. It's one of the most common types of ground faults and one of the easier ones to identify and locate. Intermittent ground faults are connections that can come and go. They may appear when the system is wet, when the resistance is low. Maybe that a wire is getting pinched by a tracking array. So when the array moves into that specific position, it's pinching the wire and causing that fault. The intermittent ground faults are typically higher resistance, and higher resistance faults can be more challenging to identify and troubleshoot. Now let's take a look at the hardware of the GFL 1500. Now this is the transmitter, it's the base unit. It has a relatively new display that is very easy to see, especially in bright conditions. It has an audio feedback feature and you can adjust the volume of that. There's an info button, which is really useful in the analyze function that allows us to see where in a string of modules a ground fault is located. We also have the mode that allows us to switch between the different operating modes of the transmitter. Then the functions of the transmitter. Analyze is the first one. It does voltage measurements and determines if there is a ground fault in the array. And we'll get more into detail on these functions in a minute here. Then fault tracing function allows us to inject a signal onto the system, use the transmitter and the signal tracing clamp to trace the exact location of that fault. And this is where the GFL 1500 is really useful in not just identifying that we have a fault, but helping technicians very quickly pinpoint where that fault is located. This tool is also category 3 1500 volt, category 4 600 volt rated. So it's designed to be used in any type of system up to a 1500 volt utility scale systems. The other two features we have are the open circuit function, which allows us to locate breaks in circuits, and mapping function, which allows us to map out a string within an array using the receiver or the signal tracing clamp. Now here's the receiver. The receiver's got an LED on the tip of it that flashes in direct proportion to the signal strength that it's getting from the transmitter. It's got a mode indicator. There are 3 different modes for the transmitter. It also has an audio alert. We can adjust the volume with that. We can adjust the modes. We can change the brightness of the display. This is also category 3 1500 volt, category 4 600 volt rated. We can adjust the sensitivity of the receiver, and we can see the signal strength both in the bar graph and in the number at the top of the display. And we can adjust the sensitivity with the up and down, the positive and negative buttons on the receiver. This is the signal tracing clamp. It's rated for use on insulated conductors up to 1500 volts. It has a backlight. It has a minimum, maximum, and average display, so we can capture readings with the tool. It also has a hold button, so if we are in an awkward position and we can't really see the display, you can hit the hold button and it will capture that reading so you can look at it more easily. We have a segmented LCD display that's backlit. Also, that backlight button, if you hold that for 2 seconds, right at the top of the yellow section of the tool, there's an LED that turns on that becomes a little flashlight there. The current measuring clamp also has a band pass filter that will filter out the high frequency component of the signal, which allows you to more easily trace the signal in systems that have high capacitance especially. Okay, moving along. Let's look at the functions of the tool and the different modes that we have as well. The analyze function is the first step in the ground fault troubleshooting process. It is going to do some voltage measurements, open circuit voltage, so it will tell you what the voltage between positive and negative is. And then it's going to measure positive to earth or ground and negative to earth or ground. And that's going to tell us if there is a fault present. If there's voltage to ground, that means there's a fault in that string or system somewhere. If there's a fault, the transmitter will give you an estimation of the resistance value of that fault. It's not an exact insulation resistance test, but it is going to give you an idea of whether it's a low resistance fault, which is fairly easy to trace, or a high resistance fault, which may be more challenging. If there's no voltage present, it's not going to be able to give you an insulation. It's just going to tell you the insulation resistance is high, above 1 mega ohm. But if it's a low resistance, it'll give you that estimation there. If the resistance is below 10 kilo ohms, the fault word will be displayed in the top left of the screen, so that you know that there is a fault present in the system. Now, in the analyze function, we have 4 categories of results. The first one is a hard fault. It's a resistance below 10 kilo ohms. It's measured voltage to ground. In this case, we're going to move into the fault function and trace the fault location. Sometimes we can have voltage to ground, but the resistance is relatively high. That's going to be more challenging to trace with the fault function, which we're going to talk about here in a minute. But we may still be able to trace it. We may have to take measures to reduce the resistance of that fault to get a better signal. The ideal result is no fault detected. I've measured no voltage to ground. I have greater than 1 mega ohm resistance. That's a normally operating system. No fault tracing is necessary in that situation. And the final result is a high resistance and high capacitance. And we get into more detail in the technical training for the GFL 1500 of what this result means, but essentially it's an inconclusive result where we had high resistance, but something was causing the voltage measurements to not measure anything to ground, and that's the high capacitance or parasitic capacitance, which again, we talk about more in the technical training for the tool. Another feature of the analyze function is the info button. If I hit the info button and go into settings and add the quantity of modules in the string, the tool will estimate where in the string the fault is. So in this left-hand example, we see that we had voltage from negative to ground, but no voltage from positive to ground. That would indicate a home run fault on the positive conductor. In the second example on the bottom right, we had a fault between 2 modules. In this case, it was between module 3 and module 4. So essentially what the analyze function is doing is automating voltage measurements that a technician would typically use to troubleshoot a ground fault, and doing some math for us to indicate where in the circuit the ground fault is located. Once we know we have a ground fault, we can use the fault function to find the fault in the array. So the fault function is going to use the transmitter to send a signal into the array, and then I can use the receiver or the signal tracing clamp to follow that signal to the exact location of the ground fault. I can inject that signal from either the negative to the ground fault or the positive to the ground fault. And having the flexibility to inject on either the positive or negative, and having the receiver and the signal tracing clamp gives me the ability to work with lots of different system types and lots of different preferred workflows. So it's a very flexible tool, allows the technician to follow that signal right to the point of the ground fault where they can very easily repair it and get that section of the system back online. The third function is an open function. It's very common to get breaks in circuits in solar arrays that I can find either with voltage testing, looking for open circuit voltage or lack of open circuit voltage in this case, or with aerial thermography. Once I've found that I have a circuit with a break, it can be challenging to find where the actual break in the circuit is. So the open function, again, injects a signal into a circuit that's been isolated to find a break in the circuit. We can use the receiver to trace the signal through the system, and when the signal stops, that's where the break is, and then we can repair that and get that string back online. The fourth function is a map function. This allows us to trace circuits within an array. So if you're working on systems where you have inadequate documentation and maybe the original installer isn't around anymore, so you don't have any documentation, you can use the map function to send the signal in through the string that's been isolated and use the receiver or the current tracing clamp to follow that signal and figure out where in the array that circuit is actually located. Excuse me. Then you can write that down in your documentation or on your array layout. Now we have a couple of signal modes in with the transmitter. We can hit the mode button to change the signal mode, and we can hold the mode button down to go from high to low signal strength. The first mode is the array mode. And this mode is used when you have more than 30 volts on the positive and negative terminals of the receiver. What the receiver is doing is it's actually sourcing the signal from the array. So it's going to increase our battery life by about 100%. Now we're going to go from about 8 hours to about 15 hours of battery life with array mode. Array mode won't work in open function since it's an open circuit, so there's no voltage present between the positive and the negative. The second mode type is the unit mode, and this is sourcing the signal from the transmitter itself. It's the default for the open mode. We use it when there's no array voltage present, because really array mode is the ideal operating mode. But if we don't have more than 30 volts present, we can't use array mode, so we have to source the signal from the transmitter. This is going to have about 8 hours of battery life, so quite a bit less than if we're using array mode. Then we've got an auto mode. And this will switch between array or unit, depending on whether there is voltage present at the terminals of the transmitter. If the voltage is greater than 30 volts, it'll use array mode. If the voltage goes below 30 volts, it'll switch to unit mode. Using auto is not the preferred use case. It is sometimes, especially when we're using the fault function, if we have it in auto, it may lead to some unexpected or confusing results, especially in systems with high capacitance. In some of the different modes, we also have a high and low signal strength mode. High mode is good for low resistance faults that can pass a good amount of current. Low mode is good for higher resistance faults that are not capable of passing as much current. And so we can switch between the two depending on what type of system and what type of problems we're running into. The nice thing about the GFL 1500 transmitter is I can set it up in many different ways. The best way is to isolate a single string and connect the transmitter up to that single string. And I can do that in a couple different ways. I can do that by either directly wiring it to the string out in the field, or I can do that by isolating circuits using fuses. And in this diagram, we've opened up all of the positive fuses in this combiner box. So it's only transmitting the signal through the circuit that has the ground fault. In this use case, I can use the receiver or the signal tracing clamp to follow that signal to the exact point of the ground fault. One thing I'd like to point out is the difference between transmitting on the positive and negative. In this example, I'm transmitting on the negative. That's where the purple outline goes. That's where the signal is flowing. If I switched this one to transmit on the positive in this example, because I have the fuses open, the signal wouldn't go anywhere because it's isolated to that one bus bar. So you really need to think about where you're transmitting in order to get a good signal. I can also transmit without isolating different circuits. So in this case, all the fuses are closed. There would be signal flowing through the entire system. And in this case, the signal tracing clamp would be the ideal tool to use to trace the signal. In circuits that have no ground fault, like circuit A and B in this diagram, the current flowing out and back is the same. So when you put the clamp around both the positive and negative, they cancel each other out. So you would read 0 milliamps. In the right-hand circuit, circuit C, when I clamp both the positive and negative wire at the same time, some of the current is being lost through the ground fault. So there's an imbalance in current on the positive and negative. And this leads to a milliamp current measurement on this circuit, indicating that is the circuit with the ground fault. Now I can continue going along that line if I can measure a pair of wires, looking for where the fault is. Okay, so that's the basics of the ground fault locator. And just to kind of summarize that section, there's 4 different features with the ground fault locator. I can analyze the system, see if there's voltage to ground, get an idea of what that resistance is. I can use the fault function to inject a signal into the system that I can trace using the signal tracing clamp or the receiver. And then I have the open and map functions, which allow me to find circuits that have a break in them, find where the break in the circuit actually is. And then the map function, which allows me to identify circuits within a system where I have inadequate documentation. And this is really allowing technicians to be able to locate and fix ground faults much faster than techniques that we've had previously. So now let's talk about the PVA 1500 IV curve tracer. This is another advanced diagnostic tool in the solar industry. So just basics of an IV curve. An IV curve measures short circuit current, which is the maximum current that a module is capable of producing, and open circuit voltage, which is the maximum voltage that a module is capable of producing. But since I don't have a short circuit and an open circuit at the same time, those two conditions cannot exist simultaneously. So what an IV curve tracer does is it measures open circuit voltage or short circuit current. Most of them start at short circuit current, and then takes samples of voltage and current between those 2 points, and then creates this nice graph. The knee of the graph, that yellow dot there, is the maximum power point. If I measure horizontally across, I will get to the maximum power current. If I measure vertically down, I'll get to the maximum power voltage. The area in this box here is the largest area of any point on the IV curve. So if I move that maximum power point to the left or to the right, that area of that box is going to become smaller. And so that maximum power point is the highest power that the module or string of modules can produce. And that's simply the voltage times current, which gives me power in watts. And that should be the rating of the module if we're working with a single module. So why do I care about IV curves? IV curves really give me the full picture of the performance of the module. Now, there are 6 different deviations to an IV curve, and 4 out of these 6 deviations I would not be able to identify if I was just doing IV curve tracing. So IV curve tracing really gives me the full picture of the performance of that module or string of modules that I'm testing. IV curve testing is most commonly used at commissioning. Especially in larger scale systems, the company installing the system is typically not going to be the company that will own it over time. So that asset owner, when it brings on this new asset, wants to know that the system is working properly. So we'll typically do IV curve tracing either of a sample of the system or possibly from the entire system in order to ensure that the modules and strings of modules are working properly. I can also use IV curve testing for troubleshooting. When we do aerial thermography, we often find problems that are areas of concern within the array. So I can use IV curve testing to determine what the actual cause of the problem is with my modular string modules. Once I've determined that cause, if the cause is a manufacturer's defect, I can use the IV curve traces documentation to get warranty claim from the manufacturer. We also see IV curve tracing used in maintenance to determine when it's financially viable to wash the array. So they'll IV curve trace a sample of the array when the array is dirty, figure out how much the power that section is making, and then wash that section and retest it to see what the difference between a dirty array and a clean array is in power production. And then they can determine whether it's financially beneficial to wash that array. We also see some asset owners using annual IV curve tracing to track annual degradation of modules. So the performance of modules goes down every year, about 1% per year. And asset owners want to make sure that the degradation rate is within the module manufacturer's warranty range for degradation. If it's not, they can do a warranty claim and get either reimbursement or replacement of the modules. So they're doing this annual IV curve tracing of a sample of the system to see how those modules are degrading over time. We have 3 models of IV curve tracers at Fluke. The SMFT-1000 is a solar multifunction tool that includes IV curve tracing. It can measure up to 1,000 volts and 20 amps, and currently it's limited to modules of about 19% efficiency or less. The 2 PVA 1500 models will measure up to 1,500 volts and 30 amps. The T model, when the efficiency exceeds 19%, the current rating is dropped down from 30 to 10 amps. The HE model is specifically designed for testing high efficiency modules, and it can test any efficiency up to 30, the full 30 rated amps. I will say that the SMFT-1000, we are working on a hardware accessory that will be out early next year that will allow it to work with those high efficiency modules. Different IV curve tracers perform the test in different ways. The SMFT-1000 uses resistance to measure the test. So it will conduct 128 test points across the IV curve sweep, and it takes about 32 seconds or so to run that IV curve test. The PVA models use capacitance to do the test, and it's a continuous sweep from open circuit voltage or from short circuit current to open circuit voltage. And you could take either 100 or 500 test points during that continuous sweep. 100 test points is perfectly adequate for most field applications, but we've had some lab-based applications where they want a really high fidelity IV curve, request 500 test points. If you're using the 100 test points, because it's a continuous curve and it's using that capacitive test, it takes about half a second to run the IV curve. So the PVA models are significantly faster than the SMFT, which is really advantageous for situations where we're doing commissioning and want to do a high volume of tests over a short period of time. The SMFT-1000 has an internal display, so I can see the IV curve right on the tool itself. It's also a multifunction tool, so it includes several other features, including insulation resistance testing, bonding testing. It's got an inspection test list. It can measure power, a bunch of stuff in one package. And it's really designed for rooftop systems for residential, commercial, and industrial applications. The 2 PVA models do not have an internal display. They need a Windows-based device to operate the tool and to analyze the data. The advantage of that is the numbering and naming convention for your assets is very flexible. Also, you have a lot of storage space in an external device. The downside of that is you need to bring another tool with you onto the roof, and it has to be a Windows-based device. The PVA models are only an IV curve tracer. They don't do any other tests, and they're really focused on the utility scale installations up to 1,500 volts, although they can be used very well in both commercial, industrial, and residential applications. So the nice thing about the SMFT 1000 is it is a small tool, it's relatively inexpensive, and it has a lot of tests packed into one unit. It does have a limitation of testing modules, less than 20% efficiency at this point. Although, like I said, we're coming out with a hardware accessory early next year that will allow us to test high efficiency modules as well. The PVA 1500 T2 model gives you 1500 volt testing, but it is limited to 30 amps if it's less than 20% efficiency, and then it's reduced to 10 amp rating above at 20% or above. The PVA 1500 HE2 is designed for working with systems with high efficiency modules. It will test all day long at high volume without overheating, without damaging the tool. The downside is it's a relatively large, and it's the most expensive tool in the IV curve testing portfolio at Fluke. Okay, let's look at the PV Analyzer software, which is the user interface for the PVA 1500 tools. This is the main screen you're going to see. You can see on the left-hand side there are 3 tabs. This is the Traces tab. It gives you the chart of the IV curve. In this example, I have both the IV curve, the measured IV curve in the dark orange, the IV curve translated to standard test conditions in the yellow color, and then the power voltage curve in blue there as well. The top right gives you your status and the buttons that you use to run the tool. The bottom, that's the top right. The bottom right gives you the readings from the soul sensor, which is the environmental sensor. So you're getting your irradiance, which is intensity of the sunlight. You're getting temperature and the tilt angle of the array, which should be equal to the tilt angle of the soul sensor. That bottom section gives me data on the test that I just performed. So performance factor is simply my measured power divided by my expected power, expressed as a percentage there. And the closer I am to 100%, the better off my system is working. The fill factor is a measure of my maximum power current times maximum power voltage, which is the measured power of the module, divided by short circuit current times open circuit voltage. Since I can't have a short circuit and an open circuit at the same time, this number is that number is kind of an imaginary number, and the fill factor will always be less than 1. It's typically going to be somewhere between 0.74 to 0.7 or so, and that can be expressed as either a decimal point, as it is here, 0.77, or as a percentage, which is what you would see in the SMFT 1000. The other data at the bottom there is the environmental conditions at the time of test. So we can see what the irradiance, temperature, and tilt angle were when we took the test. The second tab is the table tab. This gives us all the same information that was, or most of the same information that was on the Traces tab, but it's just in a table format. So I can see things like, well, first the columns. I've got my measured column on the left, a predicted column, which is the manufacturer's data converted to what it would be under the conditions in which this test was taken, and then the measured data translated to standard test conditions. And so really what I want to do here is compare the measured to predicted and see if they're similar. If they're close or relatively close, I know it's a good test. If there's a big deviation between those two, I know that there's something wrong and I need to do further investigation. The third tab is the History tab, and History tab gives me the last tests that I've done. So they're in chronological order from left to right, and I can see if there's any major deviations in these test results. And we can see here that I've got the two columns on the left and the one column on the far right are all very similar. My fill factor is 0.77, but those two in the middle, the fill factor is lower, 0.62 and 0.64. So I know that there's something a little different there that probably warrants further investigation. So I need to look into those two and see if there's any problems with those measurements. Now, when I do IV curve testing, I need to measure the irradiance and the temperature at the same time as the IV curve. And this allows me to compare different tests to each other. And so if I know the irradiance and temperature at the time of test, I can convert things to standard test conditions, and then I can compare things evenly. Without the environmental data, I can't do that. So the first thing I needed is the irradiance. Irradiance is intensity of the sunlight measured in watts per meter square. I really want as high irradiance as I can get. The ideal would be greater than 800 watts per meter square, 1,000 watts per meter square being my standard test condition irradiance. Excuse me. If the irradiance is below 400 watts per meter square, I can use that for troubleshooting, but I don't really want to use that for performance testing. The further the irradiance is from 1,000 watts per meter square, the more error is introduced into the algorithm when it converts the measured data to standard test conditions. Also, I want stable irradiance. I don't want clouds coming and going. I just want a nice, steady, sunny day. I also want a day that's not really windy. Gusts of wind will impact the temperature measurements, which will throw my results off. Essentially, the module cools down faster than the temperature sensor is capable of measuring, and I'll get inaccurate measurement results. Now, this is a picture of the Sol sensor. It's the white box on the right side there. It clamps to the side of the module. I want it at the same tilt angle and orientation of the module. The round part at the top is the irradiance sensor. There's a temperature sensor that attaches to the bottom, and then we affix that to the back of the array. So it will measure both irradiance and temperature, and then it has an internal tilt sensor as well. There's a lens cover on the irradiance sensor, so make sure you take that off before you do your testing and put it back on when you're not testing, because that is a sensitive measurement device. We have 2 thermocouple ports on the Sol sensor. Usually 1 thermocouple is plenty to get an accurate measurement. Some lab situations want 2 measurements. Make sure if you're using 2 thermocouples that you affix both of them to the back of the module, because the software will average those 2 together. So one is not an ambient temperature and cell temperature, they're both cell temperature. So if you're using 2 thermocouples, make sure you attach both of them to the module. If you're only using 1 thermocouple, which again, in most cases is going to be perfectly adequate for our testing needs, connect it into the same port every time so that those temperature measurements end up on the same column in the spreadsheet when we analyze our data. So we want to go take an actual IV curve. With the PVA models, we're going to first turn the unit on. If I press this green power button once, it'll turn it on. Pressing it once again will pause the operation, but we'll keep the Wi-Fi connected. Pressing it 3 times will shut it down. It's good to shut it down if you're moving locations to conserve battery power. If you shut it down and turn it back on, it will automatically reconnect your Wi-Fi. If you hold that button down for 12 seconds, it's going to restart the unit. It's kind of like restarting your computer. Now, the Sol sensor and the base PVA unit connect via Wi-Fi. They will do that automatically when you turn those units on. Then I'm going to use the Wi-Fi settings of my laptop or tablet to connect to the base unit. It will show up as a network in my computer. When I am using connecting to the PVA, it will take over what would be my internet connection, so I won't have internet while I'm using the tool, which is fine. You don't need internet to operate or save data. If I lose my data connection between the PVA and the Windows-based device, I'm not going to lose any data because no information is stored in the PVA. It's all stored directly on the computer. Now, when I get into hooking the tool up, I'm going to go into my inverter or combiner box. This is an example of a combiner box. I'm going to open up the DC disconnect to isolate that combiner box from the rest of the array. I'm going to test my circuits to make sure there's no current flowing through them. Then I'm going to open up the fuses on one side. If I have fusing on both sides, I can keep one closed and open up the other one. In most cases, I think you'll find that fusing is only on the positive side. So I'll open up all the positive fuses. I'm going to connect the red test lead from the unit to the positive bus bar. I'm going to connect the black test lead to the negative bus bar. Then I'm going to close one fuse holder at a time. I'm going to close the fuse holder, take a test, save the results, open the fuse holder, close the next fuse holder, take a test, save the results, open that one, and just go through the whole system until I've got all my testing done. It's important that you remember to open up the fuse before you close the next one. If I close too many fuse holders, I'll have too many strings in parallel, and I will have too much current going to the tool, which will cause damage to the tool. Now, in the PV Analyzer software, this is the Traces tab. I can see my status is ready. I go to the Measure Now button. I press that. This screen will come up with your array diagram. It will ask you where you want to associate those saved test results with. I click on that asset, hit Assign and Save, and then it will bring up the IV curve so I can do a very quick analysis there. So I'm looking at things like the performance factor to make sure they meet my expectations. I'm looking at fill factor to see if that's accurate, and I'm looking at the actual IV curve to see if it has any interesting deviations there. Okay, well, that's the end of the presentation, so we can open it up to questions. And it looks like I have one in the question box here. Oh, I got a whole bunch of questions in here. Okay. Let's see. Okay, so we talked about ground faults. Obviously, the GFL 1500 is the ideal tool for looking for ground faults. You can also do the voltage measurement manually. So you could use any properly rated clamp meter or multimeter to measure voltage. We can also use insulation resistance testing to find circuits that have a ground fault. But that's where the GFL 1500 is really ideal, because it not only tells you have the fault, but it will lead you directly to the point of the fault, which is really, really nice. Another question about they're having issues with burnt out module connections, which is unfortunately relatively common these days. What can they do to identify that? There's a couple of tests that are going to help you identify the circuit that has the problem. Aerial thermography is going to pick that up really easily. Any module that's not operating, which is what happens when you have a burnt out connector, that circuit's now open. Any module that's not operating will be at a higher temperature than a module that is operating. So we can see that whole string is out on the aerial thermography. We can also just do simple voltage checking. When you're checking open circuit voltage between the positive and negative, you should have full open circuit voltage and string there. If there's 0 volts, that means you have an open circuit. Now, locating the break in the circuit has historically been more challenging, but we can use that open function of the GFL 1500. We can attach the transmitter to that isolated circuit, inject either on the positive or the negative side, and then use the receiver to follow the signal exactly to the location of the break. So that's a really nice use case for the GFL 1500. Now, intermittent ground faults, the question is, how do I find intermittent ground faults faster? That's a good question. And intermittent ground faults, ones that come and go that have high resistance, are the most challenging ground faults to find. The GFL 1500 will do the analysis to see if there's voltage to ground, which if the fault is active, it will. It may show a high resistance reading there, but you'll know there's a fault there. You can use the fault function to figure out where the fault is located. You may have trouble tracing it because high resistance faults may not have the ability to pass much current. And so using the low signal mode and using array mode and using the band pass filter with the signal tracing clamp are all techniques you can use to find an intermittent ground fault. Okay. Okay, looks like there's one more question currently. What tests does the SMFT 1000 do? Yeah, it's SMFT 1000 is designed for the IEC 62446-1 standard, which is the standard for testing and documenting grid-connected photovoltaic systems. And in that standard, there's several different categories of tests that they need to be completed on a solar installation. The first one is the category 1 tests, or safety tests. So this includes things like a visual inspection, and that standard has very specific points that need to be inspected. The SMFT 1000 has that visual inspection checklist to that IEC standard, so you can easily say if something is passed or failed, save it into the tool, and then report that out with the true test software later. Bonding testing, making sure our non-current carrying metal parts are all electrically connected together with low resistance or low ohms. It can do that test. It can also do insulation resistance testing up to 1,000 volts. And that test, it can do regular positive to ground, negative to ground insulation resistance test. It can also do a second method where it takes the positive and negative, short circuits them together, measures that short circuit to ground, and that gives you a little safer and more accurate test because there's no voltage to ground if the string is short circuited. The SMFT 1000 will also measure IV curve testing up to 1,000 volts, 20 amps, and currently 19% module efficiency, with soon we'll be able to measure high efficiency modules with our upcoming adapter. It can measure power, so you can measure DC power, measure AC power, and then it will calculate inverter efficiency. It measures open circuit voltage, short circuit current, and polarity. And I think that's about it. And so it really is a multifunction tool. The only thing that isn't in that tool is thermal imaging, really. So it does, if you've got rooftop systems, it's an excellent, excellent option. Okay.
Great, thank you very much, Will. And we do have some great Fluke thermal imagers, by the way, too, which would pair very nicely with these tools. So if there is any interest there, definitely do not hesitate to reach out to us. Also, if any questions come up that you think of after the webinar, I know that happens sometimes, definitely don't hesitate to reach out to us. You can give us a call or send us an email, and we'll be happy to get the answers to you right away. So thank you very much, Will. That was a very informative and interesting presentation, and I think our users will be benefiting from it very much. I know I did. So thank you again. If there are no other questions, I guess we will end the webinar at this time. Everybody have a great day. And again, Will, thank you very much.
Great. Thanks, John. Thanks for having me, and we'll see you next time.
Sounds good. Have a great day.
Have a good day, everyone.